This video will show how to make a pulse echo simulation with piezoelectric actuated ultrasound transducers in water. Let's create a new project. And let's define the geometry here in the browser. You can import your step file or GDS file if you have one. But here we'll use a simple face-to-face PMUT geometry. So the first thing we can do is define some shared expressions. So these will be the parameterized, they will parameterize the geometry. So we can define first the thickness of our PMUT membrane. So PMUT stands for piezoelectric micromachine ultrasound transducer. And we could set it to 20 micron. Then we can define the radius of that membrane. So that radius membrane, and the value here will be 200 micron. Then, as you might know, you have to have some coverage of the piezoelectric electrode. It shouldn't cover the whole membrane. Typically the optimal actuation is around 2/3 coverage in radius. So that's it. Then we also want to parameterize the PMUT distance, so they will be top-down facing, and they will be at a distance of 5 millimeters. As a next step, let's define the thickness of the piezoelectric material layer on top of the membrane. And there we could, for example, say that whatever but here, it will be taken as 1/5 of the membrane thickness. And then we can also define for later use as well, the driving frequency. Not absolutely needed, but will be convenient for sweeps or anything like that you might want to do. So this is all parameterized, and this is enough to define our geometry now. So we can go back to the geometry section, and we'll draw a cylinder of, well, the radius of the membrane. So let's first draw the membrane, and it will be the thickness of the membrane also. This is it. If we want to see already how it looks, we can click on build. Next step, we will draw the piezo on the bottom membrane. So that's, oh, I can zoom in to see the membrane. So that's another cylinder with a bit shifted Z position. So all is provided at the center of the cylinder. So the radius is just a fraction of the radius of the membrane, and the thickness here, it's the piezoelectric thickness. So it's just on top of the membrane. Now what we can do is add the water on top of this. Here the membrane will be clamped at the side. Of course, you could model also the anchoring in the cavity below, but this is not part of this demo. So let's add another cylinder. So the size will be, let me draw it. We will see right away how it looks. So some radius of cylinder for the water, and then the height is really close to the PMUT distance that we asked for. And if we build this, then we will see that we have our membrane that is assumed to be in a bigger layer of silicon. So the membrane will be taken as silicon, and the silicon will continue, so there will be reflection of any ultrasound waves on the bottom side, also on the top side. On the top side there will be another PMUT, but then on the other perpendicular side of the cylinder, the waves will be allowed to go out. So it's a bit like if you had two dies of silicon with a PMUT, and they would be facing each other. and then there would be water in between. So that's good. Now we can also draw the same membrane, but on the top side. So for that, we could make a copy of the cylinders, or I could cheat a little bit here because I just know which distance and which offsets to use. So it will be another membrane with a given radius and the membrane height. So you can see it appearing at the top. So this will be outside of the water, but then the top piezoelectric material, this will be inside of the water. So this one will be shifted a bit differently, and it will have the radius of the PZT, or piezoelectric material, and its thickness. There we go. And yes, now this could be enough, but what we could do as well, if we just for visualization, we could make a cut so that we can see the waves actually propagating through the water without writing the whole volumetric data and making a post-processing clip. So this also allows us not to write the entire volumetric data if we don't want to. So what we'll do is add an extra box. It's the last operation, just to define this face that cuts through the whole geometry. And this box will be looking just like this. And now, as a last step, I just want to have the cut. I don't want to actually have the box. So what I could do is fragment all, and then I will remove what I don't want from the box. All right, and now I can use the remove operation and say that I don't want to see this part of the box anymore. And now we should be good. Now the difference is that now we have access to this face inside the geometry. So very convenient for rendering, but not really necessarily needed. As a next step, we have to define materials. So let's add them here. We will pick water first. So this and this is the water material. That's it. Now I could hide it for picking the rest. What do we have otherwise? We could use monocrystalline silicon with the actual standard wafer orientation anisotropic material properties. So these two parts form the membrane, and these two bottom parts are the membrane on the other side. So the bottom is the sender and the top one is the receiver. And that's good. And then as a last step, we define our piezoelectric material, which here is taken as PZT. So for that, PZT is this thin layer on top of the membrane, covering 67% in radius for optimal drive. All right, so all the materials are defined. Last thing we could do for convenience again is we could define a region, which would be this surface, and that would be the cut. So at any place, for example in the script, now you will be able to access this face and, for example, write the data just on this face if you want to. So this face is now known to the software. Next step, we define our physics and we set up this acoustic structure interaction with the electric drive and receive. So what do we have? We have solid mechanics. We have also electrostatics. Here we'll just be interested by the voltage send and receive, so not the current flowing. Otherwise we could take the current flow physics, but electrostatic is really what we want to use here. And anyway, like the frequency from an electric point of view will be extremely low, so electrostatic is absolutely valid and very standard to use for this purpose. As a last step, we also add the acoustic wave. So Let's add for the solid mechanics. So what do we have? Well, we don't have solid mechanics everywhere, so we have to choose the regions where we have solid mechanics. So now that I've hidden the water, well, all the rest is actually solid mechanics, so everything that is visible. So that's 8 volumes, 4 on the bottom and 4 on the top. Next step, clamp. So we can pick a clamp. So again, here you could model the actual substrate below if you wanted to, but here we will simplify a little bit. So we will clamp on the sides. This will of course affect a bit the resonance frequency compared to the reality, but it's going to be quite accurate anyways. It just depends on the level of accuracy you want. Here in this demo, this is more than enough. So the sides of the membrane are clamped, and that's it. Now the electrostatics, again, we could define it everywhere we want, including in the membrane, but as a matter of fact, the electric field will absolutely be concentrated in the piezoelectric material, and all the fringe fields will be will have a much more negligible impact. So electrostatics will be defined in all the visible regions here now, so all the places where there is a piezoelectric material. Of course, you could include also the water if you wanted to, but not needed here. Now, next thing we can do is set the ground electrode. So for that we use a constraint to 0 reference volt, and we will set it on the bottom side of the piezoelectric material. So here, here, and also the same for the other membrane, here and here. So the part that is on the membrane side. Next step, we define a signal. So here you could drive with charge drive or voltage drive. For the driving, I will just drive with a voltage imposed. So this will be on the top side of the piezoelectric layer here. And well, I could define whatever here, wavelet or a sine wave or anything myself. But what I will do is just put a dummy 1 for now, and I will actually show how you can also use the script to define any driving signal, for example a pulse or a wavelet or a ramp or whatnot, piecewise defined if you want to. So for now I just use a dummy 1, and in the script I will modify it. So that's the signal, and this one was the ground. If you put the right name, you'll also have more clarity in the script regarding what is what. Last step is we want to have a readout of the voltage. So we drive with voltage. We want to know what's the voltage when it's an open circuit on the receiver. So this guy, we want to know what's the voltage that's going to come when the pressure waves arrive on the receiver. So for that we can set lump VQ. So we will select first the phase. So it will be the part that is not the ground on the top membrane. So this is our electrode on the top side. And what do we want to say there? Well, we want to receive the voltage, so we're not going to drive a voltage there, but we still need to say something about it. So either we say that there's some circuit coupling or whatever. For example, if you have electric current flow, you could connect a RLC circuit to your receiver and see how this affects the received voltage. But what we're going to assume here is that it's an open circuit, so there's no charge that can flow in or out. So compared to the default situation, there is no charge that can come in or out. So we'll set a floating electrode, so the voltage can change, but there is no charge that can flow in or out. So 0 charge versus the default situation. Next step, we want to add the piezoelectric material model, and we want to add that on the piezoelectric, so not the membrane. So this is exactly what's visible now on the screen, so all what's visible. And then we can also set up the acoustic waves. For that, For that, two things we need to do is first select the regions where this applies. So it's the water. That's where the physics is defined. And then we want to say that there is two things. So perfectly matched layer. So as we said, we want to let so we have some extension of silicon on top and bottom. So this will lead to wave reflection. That's the default behavior. But then on the sides, we want to say that it's kind of two parallel plates facing each other, but on the sides, it can just flow out in the way it wants. And then the silicon will actually extend radially forever, but the waves will be allowed to leave perpendicularly. And then as a really last step, we add the acoustic structure interface. And that's it. So we are all set, and we can move on to the next session. For that, we go to the simulation. We add a simulation. You can add any number of simulations of different kinds at the same time. And here we're going to do several things. First, we will mesh. So in terms of meshing, lots of options. What we could use is the mesh refiner, which has the most options. And here we will use a frequency of 1 megahertz, a pulse, a sine square pulse of 1 megahertz. So that's the most powerful harmonic of the drive. And then what's the mesh size going to be? Well, you have to tune it in a way that you capture accurately enough the highest frequency you want to capture. So let's see with this in water. So you can calculate this, but in water it's 1480 meter per second propagation speed. You can actually check that here, and you can tune it if you want. So it's 1480. You can also make it temperature dependent with, for example, a capital T or whatnot. But if you compute the wavelength, then you will see that you get a number, and then typically with the default order 2 polynomial approximation that we use, if you divide this number by at least 5, then you get the max size that you need to capture accurately this given frequency. Now, of course, if you put a rectangular pulse, you have an infinite number of frequencies, so you have to truncate it at some point. But here, this will capture the highest frequency of interest for us quite nicely. Definitely the 1 megahertz and a few harmonics as well. And we can preview the mesh. So this is what it looks like. And you can see it has been refined more at the PMUT sites. Of course, you can also use structured mesh like this, but this looks like good enough for this demo. Then next step, we can define what we want to see out. So we might want to see, for example, the pressure field. What I forgot to say before this is that we're going to do a transient analysis here. We're going to use generalized alpha, second order accurate algorithm. And we will start at 0 seconds. This is when our pulse will start. We will end at 7 microseconds, which leaves enough time for the waves to arrive. I think they will arrive at 3.5 microseconds at the top, and also bounce back and see a bit what happens after they arrive and bounce back. And then the time step has to be small enough to capture the highest frequency that you want to capture. So it's a second order accurate scheme. So with 5 time steps per period, you start to be likely quite accurate. So this number corresponds to capturing correctly the highest frequency we want, knowing that we throw in lots of a big harmonic content when we don't put a perfect sine and we don't analyze in steady state. If you put a pulse or something like this, you definitely have more harmonics excited as well. But we already covered this part. Next step, then we can select what we want to see out. So the pressure field, also the displacement field, maybe. And what we actually are interested in here is to get the received voltage. So we defined this lump. It's here. So it's called lump. You can rename it if you want. But this discrete output, so this is the voltage at the top electrode, where it's a floating electrode with the disconnected floating electrode without charges coming in on it. It's reference to the ground, so this is actually going to give you the voltage drop across the PZT layer on the top membrane. And we could call it the receive voltage, because that's exactly what it is. And then as a next step, as we discussed, here we want to explore a bit how to use the scripting interface to fine-tune exactly what you want. So the first thing that we're going to do is we're going to use another drive than the dummy one that I used. So for that, what we can do is go through the script, so fairly short and concise script. And we can go to the signal drive. So here it's a flat 1 constant in time. But if we don't want to use this, then what we could use, for example, is this, and you can hover above it and you will see exactly what you're doing. So what we're going to do is we're going to use this flavor of the expression generator. So what this means is that this is a changing point in time. So after half a microsecond, the expression used for the drive will change. So initially, from 0, where we will start 0 seconds, to 0.5 microseconds, we will use this expression for the drive, so a square of a sine at 1 megahertz. And after half a microsecond, so basically half a period of the sine, then we will switch to the 0 expression. So basically we'll have a sine square volts, and when it comes back to 0, then we flatten out to 0. And the thing that decides in which of the parts of the piecewise defined expression we are is the time. So when the time t is smaller than 0.5 microseconds, then it switches to this expression. When it's above, it switches to this 0 expression. And you can define it in piecewise with as many ticks as you want, and really define the profile you want. You can also import a CSV file and use this to drive in exactly the way you want. So if you wanted to import a CSV file, the way this would work, you would go here to shared expression, you would add a shared expression, interpolated function, you would drag and drop your CSV file. And once this is defined, you can use it, for example, in the scripting interface to define exactly the profile of the drive you want. So this is one thing we needed to do because we haven't defined it graphically here on purpose to demonstrate how things go. Now a bunch of other things you can do for optimizations, and this is likely not going to be required anymore in the future, but you could check the documentation of this gen alpha function, and if you know that the matrices don't change over time, then you could just say that they do not change over time, and this will accelerate the resolution. But by the time you're watching this video, it might be that this one is fully automated and automatically checked, and you don't need to touch this. But this will definitely, as of today, provide a nice speed up. And then another few things we could do is really fine-tune what we want to get out. So do we want to get the pressure field everywhere in the volumetric way? So that will be probably very heavy. I don't know if we're interested in that here. We're not interested in that. So what we could do is we could use the cut that we defined. Now we defined it graphically, this cut region, and we can use it here, and then the pressure will only be written on the cut. So this will really show us exactly what we want without having to download or even generate a massive amount of data for each time step. Of course, you can tune anything. You can skip the write for some time steps. So this actually computes the next step, and then this is just some post processing. And then another thing we could do also is, if you don't want to write on the whole solid mechanics, you could write on the ground face of a membrane, the deflection, for example, if you again don't want to see you everywhere. This just depends on what you're interested in. And the last step we could do is print out at every time step what's going on. So you live see in the logs what is the voltage received at the receiving electrode. So you could just use regular Python and print this discrete value. So you can see definitely that this exactly corresponds to what you've done graphically. So I have defined one of these discrete outputs, and this is where it happens, and I have called it receive voltage, and this is called receive voltage. So that's about it, and we are now ready to make a run. So in terms of running, so you can use either DDM for large scale runs, so for example 100 nodes, and you can choose then 1 core per node, but here it's not a massive simulation, so we could just use 1 node with 4 cores, and you can choose the timeout you want, but here it should run very quickly, and we're ready to click the run button. So while it's starting, so if you have this default settings, it will start instantly, but for larger instances it might take a minute or up to 2 minutes to start for really large scale simulations. You can check the logs. This also applies to the mesh, and you can, if you're doing sweeps, for example, if you wanted to sweep what's going on for different thicknesses of the piezoelectric material, then you could select the thickness piezo as a sweeping variable, and then you would see in the logs, you would see one possible tab you can pick per job. So this would then allow to run a sweep of 10 variables, for example, at the same time in the cloud. Now the simulation has started running. We can check what's going on. And the first time step will take a bit longer than the other ones. And then from the other ones on, we can reuse all the matrices, so all the other ones will be much faster. Now we can see that the runs have started, and every time step is fairly quick to compute now. And I believe I have asked to get the results up to 7 microseconds. So you can see live what's going on at the receiver. So for example, after 1 microsecond, you have really no pressure at all. And based on some analytic propagation speed calculation, they should start to be pressure received after around 3.5 microseconds at the receiver. So the pressure received increases, and it will start to be non-negligible around 3.5 microseconds. Yeah, so, and then from there on, complicated things will happen that will be best visualized on the graph. So what we have done is set a kind of pulse for one period on this emitter, but then of course it was close to the resonance frequency of the emitter that we have sent this pulse, so it keeps on vibrating like the membrane vibrates a few times before like starting to vibrate less, so you actually still have pressure emitted after the first pulse on the sender. So you will receive several pressure waves on the receiver, and then things will bounce back between the receivers, of course, in the long run, and then things will start to be quite complicated and hard to see. So we'll plot that on a graph just after. Almost done. And after uploading, we can visualize the pressure field at some given time step, but we can also plot the results in Excel, for example, or visualize them right in the browser. Depends on what you want to do with the data. But let's plot this in Excel. So almost done. This is done. So the first thing we could do is visualize the results. So we could check for the pressure field. So here, not a lot of data because we have only written it on a cut. So this is the first time step, not much going on. If we want to see, for example, what's going on at around 3.5 microsecond when the wave arrives at the receiver, then we could check this and we could rescale the color in the most appropriate way. So the wave starts arriving at the receiver, and you can see that there are like extra wavelengths beside the fundamental one, because we actually have excited more than just this 1 megahertz wavelengths, because we sent something that resembles more pulse than a continuous sine wave. And even with the continuous sine waves, of course, because it's like initially starts from 0, you would also have a bigger harmonic content, but definitely the wave is arriving at the receiver there. And you could go through like all the steps to see how this wave propagates. As a last step, what we could do is go to summary and export the results to CSV file. And then we could go to this spreadsheet, and we could import that here. And we could plot this graph. All right, so here we can sort this, and then what we can do is we can select all this data and see what kind of pressure wave we get at the receiver. So indeed, you get close to nothing before 3.5 microsecond, and then you start receiving the voltage, and you get more than one oscillations, because the membranes keep on vibrating, of course, a bit depending on the Q factor. They keep on vibrating more or less after the first pressure wave has arrived. But this is concluding our kind of pulse echo PMET simulation, and we hope to see you later on in another videos.